Hi, this video will start a series of videos in which we will analyze the stationary and transient behavior of a tubular heat exchanger, sort of a long pipe with a heater inside and with some heat losses to the environment through the pipe walls, and we'll cover that analysis in quite a few videos. In particular, we will start with a first explanation of, let's say, the most simple approach, a tank full of hot water in which all the water is at exactly the same temperature. So we'll understand the basic behavior and the energy and mass balances in there. And once we have understood this basic approach, we will go to the other end in complexity and will derive the partial differential equations that govern this tubular heat exchanger, of course, assuming that my problem is just one-dimensional, and we have laminar flow, no turbulence, no stirring in the middle, because, well, the actual most faithful to real-life model would be a three-dimensional computational fluid dynamics simulation, but okay, just keep it easy, and we will be happy with our one-dimensional in space partial differential equation model, which will be assumed to be, the ground truth, the best physics can do on this, under, our simplifying assumptions. Then we will have famous particular cases, such as the transport delay partial differential equation. If the pipe is perfectly insulated and the red heater is turned off, so the temperature at the outlet is just the temperature at the inlet some time ago. We will also have the stationary partial differential equations when time equilibrium has been reached, and we'll have some exponential length solutions. So to undo those exponentials, we will find some logarithmic mean temperature difference formulas which are very popular in heat exchanger textbooks. We also try to solve the PDE with the Laplace method, and we will obtain a solution, let's say, in transfer function form, in which we will have these exponential terms in the Laplace variable, which will be, of course, the Laplace transform of delays. And then understanding that and simulating will be, let's say, the part 2 of the case study. Once we understand the simplest model, part 1, or the more complex model, part 2, then we will try to get some mixed models. We will try to have models which are first order, let's say, in time, just one state variable that accumulates energy, but we will assume that the temperature profile inside the pipe is neither constant, as in part 1, neither, a very complicated stuff changing in time as in the PDE. So we make some simplifying assumptions. Say, for instance, that if this is 100 centigrades and this is 50 centigrades, then mean temperature is 75, so a sort of linear temperature profile. Or well, we'll delve in some of those assumptions. And one exponential temperature profile will try to match the steady state PDE solution, which is the famous in textbooks, but keeping the first order time dynamics. And we'll compare the PDE solution with these first order transfer functions resulting from our approximations. Then we'll delve into part 4, in which we'll discuss the finite element approach to modeling the pipe, which basically will end up being splitting the pipe into a finite number of smaller pipes and then plugging in the first order equations of these elements we discussed in parts 1 and 3. If the elements are infinitely many of them with infinitesimal length, we will get the partial differential equation, and if we stop somewhere in the middle, we get finite elements. If we have just one element, we get the simplest models, parts 1 and 3, infinite elements, part 2, and then part 4 is just, okay, let us do some simulations with something in the middle. Let's say 4, 5, or 100 elements. So understanding how these finite element models are built and simulating them, comparing with the previous solutions, will be the objective of this part 4. And once all of that is discussed, we'll just make a video summarizing all the conclusions of these previous videos and discussing in engineering terms how to decide the complexity of the model being used. Imagine that I may have some fouling or whatever, so I have a 25% uncertainty in the heat exchange coefficient to the environment temperature. Then, is it worthwhile simulating a 300 element costly computation if I have 25% uncertainty in that coefficient? Well, that's a matter of, careful thought. And in theory, the more elements, the better. In practice, the number of elements must be justified by the trade-off between the increment of computational resources needed to handle and simulate them versus the actual benefits in my engineering application. So these kind of conclusions will be just the end case study. And well, in here you have the codes of the related videos that we can find in the channel. So I invite you to follow them one by one. Thanks for watching.